Thank you. Can you hear me? I'm so pleased to see so many of my LIGO Virgo colleagues here. I just want to thank you for making me look so good. I really think of myself as more of an icon for this collaboration, and this Nobel Prize is really something that I accept as representative of you who have made this great success in the end. I would like to highlight the fact that where we are and where we are going in gravitational wave astronomy and physics has relied on three different efforts, each of which was roughly a half a century long, in order to get where we are and where we're going. The first was discussed in considerable detail by Ray Weiss and Barry Barish, the experimental effort, and a little bit along with that, the data analysis effort. I want to talk about the theoretical effort on understanding sources of gravitational waves, the waveforms that are produced, the shapes of the waves produced by these sources, and the information that is carried by those waveforms. Then I want to talk very briefly, about a third effort that has lasted for about a half a century, a combined theoretical and experimental effort on what is called quantum non-demolition. That's a buzzword, but I'll explain what that buzzword means. And then I will move into the future, focusing on where we might be in the 2030s, the four different frequency bands that Barry Barish introduced you to, and then beyond the 2030s. So this is where I'm going in this talk. Let me just look. Okay, just looking at the time here. Okay, so I want to begin, however, with some personal remarks. I was a graduate student at Princeton in the period 1962 to 1965. My thesis advisor was John Archibald Wheeler, a fabulous man who had what seemed at the time wild ideas, most of which have turned out to be true. He was focusing, and he taught me about neutron stars and black holes. But I also was a hanger-on on the fringes of Bob Dickey's experimental gravity research group, of which Ray Weiss at the time was a member. Ray doesn't remember me in graduate school, but I remember him because he was a real intellectual giant in Bob Dickey's group, and I was sort of sitting back there as a mousy theorist trying to understand the experimental side of this subject. But I'm so glad I did, because I learned enough to, in the end, be able to collaborate with Ray Weiss, Ron Drever, Barry Barish. I was also much influenced by Joseph Weber, whom Ray talked about. Joe, I met and spent a lot of time with in the French Alps at a summer school in Les Ouches, near Chamonix. We went hiking in the Alps, and he told me all about his plans and the experimental work that he was already getting going on gravitational wave detection. And so it was quite natural that when I went to Caltech in 1966 as a young professor, that I would build a theory group that worked in black holes, neutron stars, and the theory of gravitational waves. By 1972, together with colleagues and students, I'd begun to develop some amount of vision for the science that might be done with gravitational waves, the information that might be extracted from gravitational waves. And the key idea is this, in a general form, that there are only two kinds of waves that can propagate across the universe, bringing us information about what's very far away: electromagnetic waves and gravitational waves, and that's it, according to the laws of physics. And there's an enormous difference between the two types of waves. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space as time passes. By contrast, gravitational waves are actually oscillations of the fabric or shape of space and time. Extremely different kinds of phenomena. Electromagnetic waves are generally, in astrophysics, incoherent superpositions of emission from individual particles and atoms and molecules, whereas the gravitational waves are produced by the coherent bulk motion of large amounts of mass or energy. Electromagnetic waves are all too easily absorbed and scattered as they travel through the universe, so we only see a small portion of the universe because there's so much obscuration by gas and dust. whereas gravitational waves are never significantly absorbed or scattered, even if they're emitted near the Big Bang. With those differences, it became quite clear, and I think it was clear to my theorist colleagues and students by 1972, that many sources of gravitational waves will never be seen electromagnetically. And the colliding black holes that we have seen thus far, there's been no electromagnetic signal. That surprises then are likely, and that there is a potential to revolutionize our understanding of the universe using this radically different kind of waves. So that was what we had in mind already by the early 1970s. And that was the same time, 1972, as Ray Weiss, having gone from Princeton back to MIT as a young professor, he wrote a classic paper in which he described the design for an interferometric gravitational wave detector. And he identified all the major noise sources that these kinds of detectors might have to deal with, and how you would deal with each of them, and what kinds of sensitivity you could get as a result. And he concluded that there was a real chance to be able to build detectors that could reach the sensitivities that were required by the sources that my colleagues and I were thinking about. Now, I looked at Ray's ideas, and I stated in a textbook, a classic textbook that I wrote with John Wheeler, my thesis advisor, and Charles Misner, that these are not very promising. I mean, look, he was telling us that you should build a detector that measures the motions of masses with 10 to the minus 12, 1/trillionth of the amplitude of motion compared to the wavelength of the light you're using. You measure a detector that moves by an amount that is 1/1000th the diameter of the nucleus of an atom. And an atom nucleus is 100,000 times smaller than an atom. I mean, it just was crazy. And then I studied his paper, which he didn't publish in the regular literature. He put it in an internal report at MIT because his attitude was, you don't publish something like this until you've detected gravitational waves. But he disseminated it quite widely among his colleagues. I read it, and I began to think, well, maybe this will work. I had this all-night discussion with him in Washington, D.C. that he referred to. I had discussions with Vladimir Braginsky in Moscow, and later with Ronald Drever, whom we brought to Caltech to start the Caltech effort. I became convinced, and it seemed to me that because the potential of this for human future understanding of the universe is so great, that I should do everything that I could as a theorist to help my experimental colleagues succeed. And so here I am. I and my students, in the end, devoted probably 70% of our research effort from then on to LIGO. Let me now talk about sources of gravitational waves. 1978, we had a workshop on sources of gravitational waves, gathered together essentially all of the theorists and experimenters who at that time were working in the field. Ray Weiss is here. Ron Drever is here. Barry Barish is not here because he hasn't joined into this field yet, although he did play a crucial role in helping us get Caltech into the field behind the scenes on a committee that recommended that we move forward in the field. And at that workshop, at the end, there was a discussion of strengths of sources. And this comes from the paper describing the workshop. Supernovae, where an upper limit was here, that's 10 to the minus 21. This is frequency. This is the strain that we've been talking about. Compact binary mergers, that's black hole binary, two black holes, two neutron stars, a black hole neutron star, estimated to be in this region. And so it seemed clear to us that the top goal had to be to reach a strain sensitivity of 10 to the minus 21. And so we even had T-shirts made up that said 10 to the minus 21 or bust. There is the signal that came in. The first signal was seen 1 times 10 to the minus 21. That's obviously largely luck that we were right on the money. But that was our goal beginning in 1978, and that's where the first signal came. In 1983, when we were planning LIGO, it seemed pretty clear to me that the likely first detection was binary black holes, and this is basically what I argued from then on, though I think most of the community was expecting it to be two neutron stars. But it seemed to me already then that the following would outweigh the neutron stars for the black holes in favor of black holes instead of neutron stars. The distance to which you could see a signal for two objects going around each other is approximately proportional to the masses of the objects. We were thinking at the time that the black holes we would be dealing with were maybe 10 times heavier than neutron stars. So you would see a volume of the universe that would be 1,000 times greater than for neutron stars. And that seemed to me that would outweigh the lower absolute numbers of black holes there are in the universe compared to the neutron stars. And that's how it did turn out to be. But we were very uncertain as to how strong these waves were, but we knew it was somewhere in the vicinity of that 10 to the minus 21. Numerical simulations were going to be needed, it seemed very clear to me in that era, in order to be able to extract the information from the colliding black holes that they carry. Because we could not, with pencil and paper and analytical techniques, we could not solve Einstein's equations to compute the shapes of the gravitational waves coming from colliding black holes. And so we had to do it by numerical relativity. So let me go back, a brief history of numerical simulations. This begins in the 1950s, motivated by Johnny Wheeler, my thesis advisor, who told us already in the 1950s that we should try to study the veritable storms in the fabric of space and time that occur when space and time, the geometry of space and time, are highly excited in a nonlinear fashion and rapidly changing. And we had, and he said, you go out and study this thing that I call geometrodynamics. We tried, we fell flat on our faces, we didn't have the tools to do it. But he recognized, and his students around him recognized, that in order to really do this, you had to do it numerically. So you had to begin to build the tools of solving Einstein's equations numerically on a computer or computer simulations. So the foundations were laid in the period from 58 to 64 by Charles Misner, Richard Lindquist, who are associated with Johnny Wheeler, Susan Hahn, who was a computer scientist at IBM, who teamed up with Richard Lindquist to start this out. This is the best photograph I can find of Lindquist in that era. It was not, however, until 1978 the first successful collision simulation was done of head-on collisions of two black holes by Larry Smarr and Kenneth Epley, building on foundations laid by Bryce DeWitt and earlier foundations of Misner, Hahn, and Lindquist. And there are a number of other contributors in this period. I'm highlighting the people who were really the giants in this early era. So here, 58 to 78, this is 20 years already, the struggling to get this started. Next was the problem of doing two black holes that circle around each other and spiral together, collide and merge. And the community began to work on that, and it became a very concerted effort by 1983 when we were co-founding LIGO. And we were telling our colleagues doing these simulations, we really need these simulations in order to extract information from the waves that we will see. By the 1990s, there was something called the Binary Black Hole Grand Challenge Alliance, led by Richard Matzner at the University of Texas. All of the world's experts in this getting together and working in a concerted sort of a way. And I became a little concerned that it was going more slowly than it should be, so I made a bet. I like to make bets. I made a bet that I hereby wager that LIGO will discover convincing gravitational waves from black hole coalescence or merger before the numerical relativity community has a code capable of computing the waveforms. And I wanted to lose this bet in the worst possible way. I wanted to lose this bet. By the early 2000s, I became alarmed. The progress really was slower than the experimental progress. Why was it slow? It's really hard. You're trying to simulate not two things that collide in space and time. You're simulating things that are made out of warped space and time that are colliding. So you don't have an arena in which this is going on. You're simulating the arena itself, a warped arena in which this is going on. And so by the early 2000s, I became alarmed, and so I started, in collaboration with Saul Tukulski at Cornell, what we call the SXS collaboration to work in this field. Saul had been working on this already for a few years. And in 2004, the first successful simulations were done by Franz Pretorius, a postdoc in our group, Joan Centrella, Manuela Campanelli, and their research groups. By 2014, the simulations were mature enough for the first LIGO observations. And I conceded the bet with great happiness. And when this first signal came in September 14, 2015, the numerical relativity gravitational waveform is the red here. The observed waveform is the gray, and that matched beautifully. And by comparing those waves, the theoretical and the observational with each other, we inferred the properties of the black holes and the distance to the sources. You can then go back, knowing from the observations and the comparison of the theoretical waveforms with the observational waveforms, you can go back and look at the simulations and see what was happening during those simulations. And this is a simulation of the colliding black holes as seen from outside our universe, looking in on the warped shape of space and time around the black hole. The red is the slowing of time. The arrows are the dragging of space into motion. There's a gigantic splash in the shape of space and the slowing of time. And then an oscillation. The gravitational waves go propagating out. You can also compute what it would have looked like to your eyes if you had seen the two black holes go around each other, collide and merge, creating what's called gravitational lensing, distorting the star field that's behind the two black holes. And this is a movie that was played extensively at the time of the first discovery that came again from this XSS collaboration. It was essential that we not only have numerical relativity simulations, but for the earlier parts of the waveforms, they were computed by a different technique called post-Newtonian expansion, which I won't go into detail, but that was another 40-year effort led primarily by Luc Blanchet and Thibaut Damour, and then the matching the two together by a different technique led by Thibaut Damour and Alessandro Buonanno. So that was the way we had the waveforms that we needed. Quantum non-demolition, I just want to mention very briefly because I'm also running out of time. The challenge is to monitor the motions of 40-kilogram mirrors to a precision that is 10 to the minus 17 centimeters, which turns out to be approximately the half-width of the quantum mechanical wave function of the center of mass degrees of freedom of these mirrors. So the challenge in advanced LIGO is to deal with quantum fluctuations of the motions of the mirrors themselves to circumvent the Heisenberg uncertainty principle. And this means that for the first time in advanced LIGO, humans see human-sized objects behave quantum mechanically. And that has required developing a field of technology called quantum non-demolition technology to deal with this. This is a branch of modern quantum information science. It was Vladimir Brzezinski in 1968 that told us we needed to do this, no matter what kind of gravity wave detectors we built. I didn't understand what he was saying for 10 years, and then I finally understood. And then I had my research group work as closely as possible with his research group to work out the techniques for this. I'm running out of time. I'm going to skip over my discussion of the techniques for this, except to say that the key idea, which comes primarily from Carlton Caves and from Bill Unruh, is that you take the vacuum of quantum electrodynamics, the vacuum fluctuations of light, and you modify that vacuum by what is called squeezing, and you inject the squeezed vacuum into the back end of the interferometer. It sounds just crazy, but this turns out to be absolutely crucial for the future of this field when we go beyond advanced LIGO. I want to wind up by briefly talking about gravitational wave astronomy in the 2030s. There are 4 different frequency bands that Barry Barish talked about. The low frequency band, minutes to hours, to be studied by LISA, these 3 spacecraft that track each other with laser beams. It's a ESA mission. We hope that it launches by about 2030. And LISA is capable of monitoring the gravitational waves from giant black holes, millions of suns that spiral around each other, collide, and merge with signal-to-noise ratios of 10,000 or more, and thereby capable of studying geometric dynamics with unbelievably high precision. Pulsar timing arrays, a gravitational wave sweeps across the Earth, and it speeds up or slows down all the clocks on the Earth. And so naturally, if you time pulsars at different locations on the sky, they will all slow down and speed up, or appear to slow down and speed up in synchrony, because it's the clocks on the Earth that are being screwed up. And that technique will look at supergiant black holes, billions of suns in mass. So we cover the whole range from solar mass scale of black holes to millions of solar masses to billions of solar masses. And a small black hole orbiting around a large black hole generates gravitational waves that carry a full map of the large black hole that is being explored by this small black hole as the small black hole goes around it in orbit. And here's the small black hole going around the large black hole. The orbit is wildly crazy because of the dragging of space into motion by the big black hole, as well as other relativistic effects. And it samples essentially the entire space around the big black hole and gives us then the information to do exquisitely accurate mapping of the geometry of space and time around big black holes. What are the central bodies not a black hole? For example, the naked singularity, the orbits will be wildly different, and the maps will be wildly different. So we have the capability to search for unexpected kinds of massive central bodies. I want to wind up by saying that we have the potential to study the earliest moments of the universe by the 2030s. When the universe was at an age of 10 to the minus 12 seconds, there is predicted to have been an electroweak phase transition where the electromagnetic force and the weak force come apart and gain their own individual identities, the birth of the laws of electromagnetism. And this may have occurred in what's called a first-order phase transition inside bubbles, the bubbles of the new phase where electromagnetic force does exist. In the bulk of the old phase where it doesn't exist, collide, produce gravitational waves, which today have been redshifted into LISA's frequency band. And LIGO could see similar phase transitions that would have occurred when the universe was 10 to the minus 22 seconds old, but we have no idea what was going on in the universe at age 10 to the minus 22 seconds. Primordial gravitational waves coming off of the Big Bang itself are predicted to have been amplified, whatever came off the Big Bang, amplified by inflation in the first 10 to the minus 33 seconds of the universe. Theoretical prediction that is pretty strongly believed by theoretical physicists. And what is speculated to come off the Big Bang is vacuum fluctuations, the minimum amount of fluctuations of the gravitational field that are possible. They would get amplified to make a rather rich spectrum of real gravitational waves that would propagate out, interact with a hot plasma when the universe is 380,000 years old, and put a polarization on the cosmic microwave background produced by the hot electrons at that age, which would be seen today. And so a challenge of the people who work with the cosmic microwave background is to measure definitively that polarization, thereby infer the gravitational waves that came off the Big Bang, convolved with the effects of inflation. So the spectrum that would be seen is a convolution, a combination of the effects of inflation and what came off the Big Bang. We also have the potential by 2050 to fly a successor to the LISA mission, which would be capable of seeing these gravitational waves from the earliest moments of the universe independently at periods of a few seconds. So imagine if you have the gravitational waves with periods of a few seconds, You have the primordial gravitational waves with periods of 100 million years seen by polarization on the sky, polarization pattern on the sky. Both of them are produced by whatever came off the Big Bang convolved with the effects of inflation. And I envision that by the 2050s, those will not agree. There will not be an agreement between what's coming off at periods of a few seconds, at periods of 100 million years. And there will be a huge mystery. What really came off the Big Bang? Why was it not vacuum fluctuation? So that's my dream of the future, and that at that point, those observations may really feed into understanding the laws of quantum gravity that govern the birth of the universe. So let me just conclude by saying it was 400 years ago that Galileo created modern electromagnetic astronomy by turning a small optical telescope on the sky and discovering the moons of Jupiter. It was 2 years ago that this wonderful LIGO-Virgo collaboration turned on the advanced detectors, the advanced LIGO detectors, and saw the gravitational waves from collisions of two black holes. In those 400 years since Galileo, we have learned so much about the universe with optical astronomy. Our understanding of the universe is so different today than it was 400 years ago, thanks to optical astronomy. What might be the future 400 years from now when we have 400 years in our pockets of gravitational astronomy together with electromagnetic astronomy? I think the future is really very, very exciting. Thank you.
So I would now ask Professor Weiss and Professor Barish. So if you go over to the far in the front of the stage, so you can advance a little. So, okay, turn over there. Okay.